Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome back to Learning by Solving Problem session, chapter 2, session 3. And actually in this problem we are going to combine between chapter 1 and chapter 2. In Cookle's time, cyclohexane was unknown, and there was no proof that benzene must be a six-membered ring. Determination of the structure relied largely on the known number of mono-substituted and disubstituted benzene, together with the knowledge that benzene did not react like a normal alkene. The following C6H6 structures from 1 to 5 were the likely candidates. Show where the 6 hydrogen atoms are in each structure. The first one, the cyclic structure, 6-member ring. The carbon is tetravalent. We have here each carbon has one single bond and one double bond, so 3 bonds left, one hydrogen in each. Okay, the next structure, here we have carbon, double bond, so we have 2 hydrogens. Here is hydrogen, 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 hydrogen. Each one of these has 2 hydrogens. The one internal carbon already, each one has 4 bonds, one double bond and 2 single bonds. So the prism here, each one has an H. Again, each one has an H. For each structure, draw all the possible mono-brominated derivatives that would result from randomly substituting one hydrogen with a bromine. Benzene was known to have only one monobromo derivative. Yes, that's one. For this structure, will be all the same. Okay. For this structure, we can have this Br, we can have this Br, we can have this Br. So we have 3 different monobromo. So this structure is not acceptable. We can take it out from the probability now. Okay? For this structure, okay, we have one monobromo, that's right. For the prism, yes, we have one monobromo, they all identical hydrogens. For this structure, we have 2 possibilities, either one in here or one in here. Of course, this is equal to that, and the bromo out will be equal to all of this, right? So how many? We started with 5. Now for the monobromo, we eliminate 2, and we have still 3 possibilities to go. For each of the structures that had only one monobromo derivatives in part B, draw all the possible dibromo derivatives. Benzene was known to have 3 dibromo derivatives, but resonance theory was unknown at the time. For the Kugel structure, as we can see here, we have 2 bromo ortho, and they are on single bond. Here they are on double bond, meta and para. Kugel defined his structure by proposing that between the first 2 isomers, very rapid equilibrium that we cannot isolate them. So the next structure, we can have Br, 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 Br up, down, down, down. So we have four possible structure. So for that, we can eliminate it out of the probabilities. For the prism, we have Br, 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 we have Br, Br. So we have three isomers, okay, which is in agreement with the finding three isomer for dibromobenzene. Determine which structure was most consistent with what was known about benzene at the time. Benzene gives one monobrominated derivative and three dibrominated derivatives, and it gives negative chemical test for an alkene. Well, the only structure consistent with the three isomers of dibromobenzene is a prism structure called Landsberg benzene or Prisman. It gives a negative test for alkene, but this structure consists of three member rings and four member rings, which are highly unstable. So this compound is unstable. Prisman derivatives bearing bulky substituents have been available for more than 3 decades via photolysis of strictly the benzene derivative propose a mechanism. So when we have here tertiary butyl, this molecule is a little bit out of plane. With UV light, you can get these two carbon coupled together in electrocyclic reaction to form the diwer benzene structure. And then this diwer benzene structure under 2+2 cycloaddition form the Prisman. See you next session.